Okay, so light and atoms. So, slideshow. Okay. What does TYSK mean? Things you should know. So, what we have learned in theory from the lectures that you guys have already watched is that electrons tend to go in the lowest energy states available. But sometimes electrons can gain energy and be promoted to higher energy levels. So when electrons change energy levels, light is usually involved. It's either given off or taken in. We actually get much of our information about the energy levels that an atom has based on this absorption or emission of light. I know a lot of you guys, the classic sort of way that we show this is the flame tests. So you guys remember you stick like something in a solution that has like sodium or potassium. You put it in a flame, and yay, pretty colors. It's also where fireworks come from, where you get the pretty color from fireworks. It has to do with the substances involved. But we're going to talk today about light. So light is actually a really neat topic, because there's a lot of weirdness that goes on with light. So evidence that light acts like a wave. So when I think of a wave, you think of like something like that. So there's evidence, experimental evidence, that light behaves like a wave. The first is reflection. So if you shine light at, say, an incident surface like a desk or a piece of metal, at a given angle, it'll bounce off, and these two angles will be the same. So that's one piece of evidence that light is a wave. Not a really convincing one, but one nonetheless. Does anybody remember what happens when you shine a beam of light into water? There's a word that happens. Refraction, yeah. Light refracts, which only waves would do. So what is refraction? So if we have, I can even use colors. Color blue. We have like some water and I shine an orange sunbeam at it. It's actually going to change directions. And it'll change at a specific angle, index of refraction. You don't need to know any of that. Does anybody know why it changes angles? This is not important, nor do you need to know it for this class. Yeah, Don. Okay, so it has to do with something like the molecules are closer. It does. The speed of light that we know is 3 times 10 to the 8th meters per second is true only in a vacuum. The speed of light changes in certain media. In fact, there have been researchers who now have been able to stop light. They get it really, really cold, and they can stop it for like a microsecond. And then they can't control it anymore. Really neat stuff. The reason they want to do that has to do with, have you guys heard of quantum computing? It's like getting computers down, like going even smaller to like the quantum level to process information. Polarization. Polarization. If you get light shining, if you have polarized sunglasses, right? It's light shining at you, and the waves are moving in all kinds of different directions. What polarization does is it only lets one direction of that wave to go through. So if you have waves going like up and down, and then sort of, wow, those of you who are at home can't see this, but imagine Mr. Bennett making motions like side to side and up and down, and like at different angles. So polarization means that it only lets one of those directions of waves go through. So this is all evidence that light is a wave. However, there is a much more easily visual one that I'm going to show you a video about in a second, and that's called interference. So light will interfere with itself, like waves will. Now, I apologize to those of you who have seen this before. It's still really neat. This is yeah. And this is Dr. Quantum's double slit experiment. It's gonna, at some point I'm gonna stop it and say this is what you need to know, and then the rest is gonna be like mind-blowingly weird. You don't need to know it, but I think it's really cool for you guys to get this base down. And I actually have to put the microphone next to the speaker. I in no way endorse Mote X lazy phone. Where is this? Hold on, guys. Does anybody have a PC? Ah, I got it. Never mind. All right.
We first need to see how particles
All right. So, other than that guy being a little creepy, I thought that was interesting for us to watch. There's a lot of the math that goes into that I don't get. But merely by observing what happened, we change the outcome of the experiment, which I think is sort of mind-blowing, right? Okay, so now back to notes. So now that you have observed the double slit experiment with waves, like waves of water, you can see that the same thing happens with light. So here, in the double slit experiment, the slits were changed from being vertical to horizontal, and the light went through. And so by shining light through these two slits, we get the interference pattern we would expect from a wave. So we have very solid evidence that light acts like a wave. But wait. Oh, so this is what it'll look like. You see from the two slits, you have in the middle you have the strongest intensity, and then it slows down, or it gets lower. I mean, but then you have these gaps. Oh, black on black, no good. Then you have these gaps between them where the waves cancel each other out. So you have very strong evidence that light is a wave. You can look at that. These are all pictures that will go up. Lots of other visuals for you to see that light acts like a wave. They keep coming. I actually have your note packet that I did all my little notes on. I forgot that that a couple more slides were added in. So we have all this evidence that light is a wave. However, light is a particle. Newton was convinced light was a particle because it moves in a straight line. So, possibly the smartest man who ever lived was convinced light was a particle because it moves in a straight line. There's also something called Compton scattering, not something you need to know about. This totally is if you're really interested in light and want to go deeper. And this has to do with the collisions between them. So particles will collide in a certain way, waves will collide in a certain way. Compton scattering shows that the collisions act like they're particles. However, the most important evidence of light being a particle comes from something called the photoelectric effect. So, the photoelectric effect is seen on this slide. So when scientists shined, what's the correct, shone? How about exposed? That's better. Exposed light to a surface. They found that they could get electrons to be ejected from that surface. And they could measure the electrons that came off the surface of this material. Sodium is a very popular one that was done with this. Now, I want to play around with the photoelectric effect for a minute. And let's see if you guys, as chemists, can determine some of the results that they pulled out of this. So, if you're watching at home, you can just sort of fast forward until the simulation comes on. Everybody having a good first full week? Yeah. Getting into the flow a little bit? It does sort of feel like it's already the response. It feels like it's the middle of the year. It sort of does. I like that though. I don't know. You know, it's cool. We work in a place where I can't speak for every teacher, but so many of the teachers are like super excited to be here. And so like we sit in the lunchroom and like we talk about how awesome it is to be back. And, like, I don't know. It's just fun. I will say that was not the case at my old school. Okay. So we have a system here where we have a surface. Obviously, it does not help those of you at home if I am pointing to things on the board and you can't see. We have a surface of sodium right here. So this is sodium, and we can shine a light on it. And I'm going to shine, I don't know. Let's shine, oh, that's intensity. Oh, no, don't do it. Okay. I'm going to start with some red light. I'm not going to play with the battery at all. The battery can just change some things. I'm just going to play with the light. So I'm going to bump up the intensity of my light. I'm going to shine some red light. That actually looks kind of purple. Does it actually change color? No. Okay, so I'm going to shine some red-looking light. Now, I'm shining some light on my sodium. Is anything ejecting from the sodium? No. So let's talk about energies of light. We're going to get to this in a minute. What has more light, UV or infrared? Yeah. Energy is UV. UV has more energy than IR. The way I remember this is that what's the type of light that gives you skin cancer? UV, right? You can sit under IR all day. Me, especially being super pasty white, if I go out on a hot, sunny day, I need to like swim in sunscreen because the UV can damage your DNA. So I remember, okay, I'm afraid of UV light. That means that's the one that has more energy. So that's how I remember the difference between high energy, which is UV, and low energy, which is IR. So I'm shining this light, and now I'm going to draw this up on the slides in a few minutes, but I'm bumping up my intensity. So for those of you watching here, I'm going to draw on the board what this means. I don't have a marker. All right. So I have red light, and red corresponds to a certain wavelength. So I have this certain wavelength here. How does this change when I increase the intensity? The amplitude goes up. So I have the same wavelength, approximately the same wavelength. No, you have exactly the same wavelength. What I drew has approximately the same wavelength, because I'm a terrible artist. So your wavelength and frequency do not change, just the amplitude. So if you think of waves in an ocean, the amount of waves you get hit by would stay the same. You would just get hit by bigger waves. So those of you who have gone to the Cape, if you're on the inside, the bay, you get these really tiny waves, but they probably hit you just as frequently, right? But if you go onto, the ocean side during like a hurricane, the rays will probably hit you with just about the same frequency, but the intensity will be much higher. Okay. So it doesn't matter. I'm shooting some really high intensity light at the sodium, and nothing's happening. So I'm going to drop the intensity down. I'm going to go, let's go to blue light. What do you guys see happening now? So these blue dots are moving across. So these blue dots represent electrons. Okay. So what's happening is we're shining light at the sodium, and it's ejecting electrons across this, what I guess is a circuit, right? So electrons are going, they're being attracted to the positive end. Now let's drop my wavelength even more. What do you notice happening to the electrons? They're getting faster. They're moving more quickly. Did I change the intensity at all? No. All right. I just changed the frequency. So now let's move back here. So we know that UV light, let's get it down really low intensity. Very low intensity. Are the electrons still moving quickly? But what changed? The amount of them. I get a lot less. The speed didn't change. Just the number of electrons that ejected changed. So let's go back here. I figured out the... Okay. I'm going to bump up the intensity a little bit. So I'm in green light. Am I still getting electrons? What does their speed look like? They're very slow. Now I'll keep going up. Now what happened? No more electrons. Let's bump up the intensity 100%. Still no electrons. There is a cutoff. So when scientists first looked at this, they thought about it like waves. So think of a boat in the ocean. And they thought, oh wow, if we increase the intensity, we'll get all these bigger waves. And those bigger waves will rock the boat and knock those electrons out. Turns out that that doesn't happen. Scientists were shocked. All that matters was how quickly the waves were coming. So it'd be like if you were on the ocean and you just kept getting hit by these waves and all of a sudden a boat shot right up into the air. It was really, really surprising to scientists that this is the way it worked. Now, let's find, I'm going to keep the intensity high so more electrons come out. So it's right around, oh, I think we found it. Somewhere around 540 nanometers of light or below in wavelength is what is required to knock an electron out of sodium. Not something you need to remember. But just remember that it is not the intensity of light that matters. It is the wavelength of light that matters. Yes. Yes. Yeah. Okay, so the question was about Dr. Quantum and Dr. Quantum stating that as we observe, the wave functions collapse, don't act like a wave anymore, they act like particles. I do not know the answer to that question, just to be honest. Mm-hmm. Mm-hmm. Yeah. Yeah. Mm-hmm. Yeah, so all observations change the system. Yeah. I don't know if this observation in particular collapses the wave functions down to a particle. That might be the case. So one last thing I want to show you is as we drop the intensity down, in theory, yes, there we go. Okay. We just get a lot less electrons that bounce out. So intensity tells us the number of electrons that come out. Wavelength tells us that they will actually come out. Now I want to show one graph. Okay. So here's what happens. If I decrease my wavelength, that means I have higher energy light. And let's just bump up the intensity a little bit so we can see it a lot more. Maybe a little more. Okay. So if I increase my energy, we already said that the electrons just move faster, right? So it turns out that you need a specific amount of energy to eject an electron from a given substance. It's not the same for every substance. This just happens to be for sodium. Any extra energy that that light gives to the surface, where do you think it goes? It's not heat. Did you have a hand, or is that? The speed of the particle. So any excess kinetic energy from the light goes into the speed of the particle. So this graph shows the energy of the light versus the speed of the particle. Sorry, I can't. Watching at home, the graph that's up on the board shows you the energy of the light versus the speed of the particle. If I increase the energy of light, it goes up linearly. But you'll notice that, wow, those are really whipping. You'll notice if I go beyond that critical wavelength, which I forget what it was, 540. So if I go beyond that, my graph stays at 0 because the electrons do not get ejected. There's a specific amount of energy required to eject the electron. Okay? Any extra energy from light just makes it go faster. So this was really confusing to scientists, and we only have 2 minutes left to explain it. All right. So let's quickly, if I know where I put the, all right. Okay. Mr. Hamill's trying to get me to use the clicker, which I've never used. And now I can't. Oh, right here on the edge. Okay. So let's explain this weirdness really quickly, and then we can leave. So it's the difference of intensity versus wavelength. And we're going to see that wavelength and frequency are related. So with the red light on sodium, no matter how intense, no electrons escaped. With violet light, or even better, UV light, even with a low intensity, electrons were ejected. So it goes back to, we'll get to that part tomorrow. The question was, how does this prove light's a particle? We'll get to that part tomorrow. So we have high intensity and low intensity. But what we're really concerned with is the frequency. So this is amplitude, which is a measure of intensity. But oh my god, that's the worst wave I've ever seen drawn. All right, but what we were really interested in is the frequency. Okay, and so this is the weirdness. Tomorrow we will explain the weirdness. They expected high intensity light to knock off electrons. It had nothing to do with intensity. Intensity only made more of them come out, if they were going to come out at all. You needed a specific frequency. And tomorrow we'll explain why that shows light's a particle. Okay, I'm actually after school today. If any of you want to come and do work on like the lab, I know you have like a week and a half. But if you need like a computer, you need Excel help, I'm here for that until about, 4:15. Pick up problem set 2 on your way out the door. Get started early. Next Wednesday, so a week from today. And other than that, have a wonderful rest of your day. I'll see you tomorrow.